Yes. I am waiting. I am still waiting.
I think a lot of people are arriving, so...
Yes, yes, we can wait. But we already have 38 participants, so maybe there is one or two or three among them who
want to say something.
want to say something, yes? I would have a question, but the question is for Karl Mangieri, who is not here, if I'm correct, but maybe the question could be answered by others. I see Jan-Hendrik Evertje is among the audience, and maybe...
Oh, yeah, sure, yes.
Yeah, you are here, Jan-Hendrik?
Yes.
Oh, that's nice. Hello.
Oh.
It's very good that you participate. So my question is, Kalman yesterday pointed out the result of, I think, Koymans concerning a Catalan equation for finitely generated domains.
Yes.
What is the method used by Koymans?
Well, it's more or less the method was more or less pointed out by Kalman. First, you have to do it over a number field.
Okay, so it's in fact the so to say the general method. Kalman pointed out.
Yeah, it's basically over number fields an extension of the Rot-Tiedeman's method. So linear forms of logarithms, both in the ordinary p-adic case, you have to do it over the s-integers. And then, well, yes, with the specialization method, which was mentioned by Kalman, you can extend it to finitely generated domains. So with specialization method, you can more or less map the equation over finitely generated domains to the Catalan equation over the s-integers. And then, okay, you have effective results. So you can compute effective bounds for solutions over the s-integers. Hello?
Yeah, and the bounds are more or less completely explicit.
Well, you can make them explicit. There are some absolute constants which have not been computed.
Okay. So there's nothing special what has to be used for this equation?
Well, no, just linear forms of logarithms for over the algebraic, over the s-integers, and over the number fields, and then with the specialization method, you can extend it to finitely generated domains.
Okay, yeah, thank you. I thought there is something special which has to be used at this place. Okay. Yeah, are there other questions? No. Additions to lectures. Problems. No. Joel, do you like to say something?
Yes, even maybe a suggestion, because I think this is not the last conference in this form of virtual conference, so whatever can be discussed about it, if you have some suggestions, it's also useful.
Yeah, that's a good question. General suggestions for how to do such a conference, how to proceed. Do you have ideas? Because we were in a hurry. We had to fix everything within a very short period. So maybe there are general suggestions. No general suggestions. Oh, Nikolai is typing. Now people are typing. I am almost happy. Yes, Mark, you can share with picture. I asked Guillaume how to do. I can try to do it myself, but I have to find Mark Munch. Maybe he's sitting very close to.
I just took picture of some very easy problem, but it's easier if I show what I wrote.
Yeah.
I don't know in this big blue button where I can do it.
Wait, you have to. Do you have a camera?
Yes, but might be not clear if I just show you. Can I share my screen in some way?
Robert, I think you can put him.
I can make him to the moderator.
No, you can make him presenter.
No, I say make him to the moderator, and I do that now.
Okay.
Mark,
he is presenter. Mark is presenter.
I have some tools now. Okay, let me see.
Okay, great.
Aha, now it okay. Thank you, Guillaume. Thank you, Guillaume.
I don't know where is this. Plus, maybe.
You have to push on the button on the right.
Where is
the bottom of the screen? At the right, just near the webcam button.
And where can I do here?
When you click,
I have annotation, something like. I cannot share something. Or at least
non, Marc, normalement, tu peux partager ton écran en cliquant sur le bouton à droite en bas.
Oh, I have it now. So wait. Okay. I will try to. Sorry, it takes a bit of time. Should open this.
I think in the meantime, Nikolai wants to say something.
Yes, okay, please, Nikolai.
Okay. So yes. When I was when I was trying to say something for the first time, it turned out that I lose the connection. So I want to say, as for some general suggestions, I want to say that maybe it is reasonable to have some kind of rooms for conversation in very small groups.
Yes, Nikolai, that is possible. this is possible within this system, but we didn't try it because of maybe complications, but that's definitely possible.
Yes. Okay.
And if you like to do this in the next few days, we can try to install it.
I think we should try different opportunities. So let's try. So
okay,
maybe...
I will discuss it by email with Celine. Yes, so we had this idea also in Marseille. Yes.
Okay, and also I want to formulate a problem, but it is rather a problem for students, but I'm not sure. My students are not able to solve it. Also, I am not able to solve it myself, at least in a reasonable time. So maybe I write a problem. It seems to me that it sounds not very bad.
That's a good idea. So we have to fix. I think Mark. I can see. I see on the screen some written formula. Is that Mark or is that Nicola?
It's me, but is it readable?
Oh, wait a moment. Not very good, but I will try it.
I don't know, like
Somebody
it's a picture.
Start.
Yes, it's readable, definitely.
Well,
it's readable?
Yes.
So maybe I can start to discuss.
Yeah, please, Mark, start, and afterwards Nikolai poses his problem. Yes? Is that fine, Nikolai?
Yes, for sure.
Good.
Yeah, it makes it complicated online. But... Okay, so it's a very simple problem. So you take a polynomial with real coefficients of degree bigger than 3. And you want to count the solution, which is kind of energy. So you count Pn1 plus Pn2 minus Pn3 minus Pn4. Very small, so smaller than 1. And you count all the solution when you take the first n values. So if you would have like some polynomial with integer coefficient, usually you will count like this thing to be 0. And it's like something not hard to do. But here you have real coefficient and you want to bound this. So trivial, this thing is between n2 and n4. And I would like to know if you can get better bounds, like something, you should expect this to be like the diagonal plus a bit more. So something like n squared plus epsilon. But even if you can prove something like n to the 5/2, would be interested to see. So this has a connection with my recent work with Christoph Eisleitner and Daniel Elbaz about percorrelation of real sequences, where this is one of example is to take polynomial sequences with real coefficients.
Okay. Yes, thank you. Are there comments to that problem?
So maybe I add one comment. If you take your polynomial to be in Z, you can easily prove it's n squared plus epsilon. And we can also prove it for degree equals 2.
Yes. Are there other comments? So now I have problems to remove my full screen.
I will stop sharing if it's okay.
Yes, please. Thank you very much. I see now there is Daniel Elbaz saying it's fine. Okay. Okay, there, Celine, thank you very much. She is answering the question of Nikolai to creation smaller rooms. We had the idea, the billiard room, So maybe we can make this available tomorrow for small group discussions. Yeah, to answer Philip Habecker's question, yes, this is also a good suggestion. We should keep the problems on some page somewhere. So my question to Guillaume is that, do you record the problems, the slides?
Yes, yes.
Okay, then we can make them available. Thank you, thank you. Okay, maybe there are few further comments before we start with Nikolai. Yeah, there are answers. Answering questions of Bruno Martin. Why is it easy? Here, this question, and this question already is answered by both of them, by Mark and by Daniel. Bruno, are you satisfied? Yes, he's satisfied. Joël, whom should Olivier Robert help?
Mark.
Ah, okay, good.
because
that's what I got. Yeah.
Because actually this type of spacing
okay,
problem,
so this is mathematics and data transmission.
I could explain just
Yeah.
this type of spacing problem is very classical in exponential sum problems, and I think Olivier Robert should know how to do that almost immediately.
Yeah.
Yeah, we actually use Olivier Robert results for n to the theta. So that's true. Like his paper about exponential sums.
Yes, but
which is
if you speak with him, maybe he also knows to answer the question not in the paper.
Yeah, right. We exchanged email already, but
okay.
So far, no solution. But
yeah, Gerald, wouldn't be technical to have a discussion, seeing everyone and by voice. Yeah, that should be possible to see the people presenting. I don't know how to fix it fast. Guillaume, is that possible that when we ask Nikolai to present his problem, that we can see him?
I can write on a screen if you give me. I can write.
Yes, but we want to see you.
Can you put your camera?
Okay, I will try.
Nikolai, you have to put your camera.
I'm here.
Yes, great.
Yes.
We can see you.
Okay. Okay, so I think 1 moment. I should be. Okay. I will formulate a problem. It may be easy, but not very trivial, and I'm almost able to solve it. However, I think it has a nice formulation. So let's A and B, alpha, beta, be real, okay? Alpha, beta, be real. To prove that there exist infinitely many Q natural such that Q divides the sum of squares. This is square plus beta Q square. Here, sum of squares and these brackets mean integer part. Do you see the problem? Is it clear? Is it clear?
Yeah, that's clear.
Is the formulation clear? I am almost able to do this. I am almost able to solve it, but what I'm explaining what I do mean by almost. Look, so we can have integer part, ordinary integer part, or upper integer part. Here we have two places, the first one and the second one. We can put in both places either both lower integer part or both upper integer part, or sometimes in one place lower integer part and another upper integer part. So we have three combinations. I can prove that at least for one combination there exists infinitely many Qs. It follows from something like Klein-Bock-Merrill theorem about approximations on intrinsic approximations on spheres. But for just for integer part itself, I don't know if it is true. So I believe that it is true, but I cannot prove. So it's a very, in my opinion, it is very nice formulation, and it is very pure, as it is a problem itself. I'm sure that it will not lead to progress in general mathematics. However, I think it could be nice.
Okay, yeah, that sounds a nice problem, definitely. Are there comments on that?
I will be happy to know the solution.
Yeah, there is a comment, a further question of Philip Habecker. Can you read it, Nikolai?
In my proof, it does depend. For alpha beta, there exists a combination. Yes, yes. In what I can prove, combination depends on alpha beta.
Okay. Further comments, questions to that?
Moreover, I do not believe in a proof in this fact when we have more than two squares, maybe five squares. I don't know for 3, but 5, 9, or for many squares, I think the answer is negative.
Further remarks to that problem? Okay, so Nikolai, thank you very much. Do you have another problem, or should we ask other people?
To start, so I was not the first, but I just wanted to start, as nobody wants to. So I think I will formulate just this problem now.
Okay, so thank you very much. So,
as for other ones, I need to speak. I think I should give opportunity to give a talk to somebody else.
Okay, so please ask questions, formulate problems, give hints to the organizers how to do it better. Okay. It seems at the moment no further questions. So Nikolai, you can formulate the second problem. Please.
So I have many problems.
Yeah. If you have many, you just have to apply the axiom of choice.
So if necessary, I can speak. I can formulate another problem.
Please.
Okay, okay. So, but I'll try to clear the screen. So, one moment. It is not very easy to work with this system. Okay. One moment. I'm sorry. I pressed something.
No problem, Nikolai.
I pressed something wrong here, and now I cannot understand. Okay. Now it's here. Okay. Does anybody knows what is Minkowski function?
Yeah.
So
you mean the question mark function?
Yes.
Yeah.
I can formulate two problems about Minkowski function. One function is question mark, another one is not question mark function.
Okay.
However, this problem is not very popular, but it is so. What is question mark function? We have Stern-Bracco sequences. So we have 0, 1, and 1, 1, and we can add numerator with denominator. So here will be 1/2, and so on and so on. It's Stern-Bracco sequences. And so here's 1/4, here's 2/3, and so on. So if Fn is Stern-Bracco sequence, then we can consider the distribution function. It means that we deal with the number of elements of Stern-Bracco sequence up to x divided by the complete number of elements Stern-Bracco sequence. And the distribution function is so-called Minkowski. This is here I would like to write a limit when n goes to infinity. This is Minkowski question mark function. It is a strange function which is monotone. Monotone function is differential almost everywhere by famous Lebesgue theorem. It has stable points, 3 trivial stable points, 0, 1, and 1/2. It is possible to prove that in rational points the derivative is 0. So if I look for other stable points, it is obvious from continuity that we have at least two stable points in the interval 0, 1/2 and 1/2, 1. The folklore conjecture, which was formulated, I think, only in my preprint, that these 2 points are just unique points. So we have just 3 rational points and just 2 more points, which are fixed points of Minkowski question mark function. I mean, the solutions of this equation. So this problem, I think, is not so popular. However, I would like to say that recently my students were able to prove that if we have the smallest point in this interval or the largest point in that interval, so stable point, so x0, then it is not very good approximable. So I mean that always happens q square and here log q. So however, if we the main problem problem is to prove that there is no more stable point, no more stable points, but these three rational points and these two irrational points. However, we do not know if there are just 2 points. Maybe there are more points. By the way, that there exist just 2 points is obviously, this is a computer evidence. So the problem to study integer stable points of Minkowski function and to give a good bounds for irrationality measure. Probably these stable points are typical. I mean that partial quotients for them should be unbounded. So I think I said too much, and I think somebody else should continue.
Yeah. Thank you very much. Many thanks, Nikolai. Yeah, are there comments on that or new problems? New problems, comments, general remarks. Yeah. I'm waiting. Joel, do you want to say further hints or?
Sorry, I am out of ideas.
Out of ideas, yes. No, we organizers shouldn't pose problems there. But maybe you want to have a further coffee now. Then we make a break until the next lecture.
We can do that if nobody say something in the next 2 or 3
maybe that's a good idea. And maybe I don't know if you got it, Joel. I said to Igor that we should start tomorrow 10 minutes in advance. So
okay.
9:20.
Yes, okay. I will do that.
Please, but then we have again the possibility for discussions.
Yes.
And I would like to ask Celine, maybe we can fix some further discussion room, virtual discussion room for small groups, and we can announce that tomorrow.
Yes, I think it would be fine. So maybe some people would have to have some more personal chats or whatever.
Of course, I hope it could be managed that this discussion room is also open next week, for instance. Because then we can continue these discussions.
Yes, if it would be possible, I think it's a good idea.
Yeah, formally I have the workshop next week, and so this is just a part of it.
I think once it has been set up, it's not very complicated. Probably.
No, I don't think so.
But, let's hope it's possible.
Yeah, so, okay, there are still... Yes, that's possible by Guillaume. So thank you very much, Celine and Guillaume. And thanks to all contributors. Thanks to Joel that he will start tomorrow 9:20 with further discussions. And I take a coffee now. I hope you can do the same if you like coffee or tea. And we meet in about a quarter of an hour, so just before 3 o'clock in our Luminite time. So thanks and see you in a few minutes. it's 3 o'clock, and it's a pleasure to introduce Attila Perces from Debrecen, and he is speaking, as you can read here, on Diophantine equations in separated variables. So please, Attila, start.
Thank you very much. Greetings to everyone. First of all, I would like to thank very much the organizers to offer us this possibility. Of course, we all know that the best way to have a mass conference is to meet together in some place like Marseille. The second best thing is when this is not possible to have a virtual conference. So thank you very much for making the effort for this. So the plan of the talk is, after a short introduction, I will say a few words about the Biluti theorem, and then I will address 3 topics in which, with some co-authors, I have a few results concerning Diophantine equation in separated variables. Not all of them are connected to the Biluti theorem. There are also some results which will be effective results. So first of all, if we take a Diophantine equation of the shape fxy equals 0, where fxy is a polynomial with rational coefficients, then in principle, the main question may be how this, or when this equation may have finitely or infinitely many solutions. And of course, we know that if fxy is irreducible over Q, but it is not absolutely irreducible, so it's not irreducible, let's say, over C, then fxy equals 0 has finitely many rational solutions. Denoting by G the genus and by D the number of points at infinity of the plane curve fxy equals 0, in 1929, Siegel answered this question quite completely. In principle, his result says that if fxy is absolutely irreducible and G is larger or equal to 1 or D is larger or equal to 3, then one has only finitely many solutions. So Siegel's result is very helpful when the polynomials are given explicitly or when they are of a very special form. But in principle, it was for a long time a question whether we can describe all the pairs of polynomials f and g for which fx equals gy, which is a special case of the previously shown equation. The case when the variables are separated, x is in the left-hand side, y is on the right-hand side. Can we describe all the situations when this may have infinitely many solutions? In the type of equations with separated variables enter many important special cases, many important classes of Diophantine equations, like superelliptic equations, hyperelliptic equations, Schinzel-Tiedemann equation, power values in arithmetic progressions, or power values of the sum of case powers, equal values of lacunary polynomials, and several other classical and important Diophantine questions. Now, the question of describing all pairs of polynomials such that the equation fx equals gy has infinitely many solutions has been solved by Bilo and Pihi. In principle, this is a widely known and appreciated theorem, which became a very important tool in Diophantine number theory. They proved that if f and g are polynomials with rational coefficients, which are non-constant, then the following 2 statements are equivalent. Equation 2 has infinitely many solutions in rational numbers with bounded denominator. In principle, it's a kind of generalization of the searching for integer solutions. So this statement is equivalent to the fact that f is composed of 3 functions, 3 polynomials, and g is composed again of 3 polynomials, where the inner polynomials are linear polynomials, the middle polynomials form a so-called standard pair, which on the next slide I will show how they look like. And phi is just a polynomial with rational coefficients, and it also has to be assumed that the equation fx equals gy does have infinitely many solutions in rationals with bounded denominator. So in principle, this is a very concise description of all the cases in which it is possible that this equation does have infinitely many solutions. And there are the possible pairs for G and F, or F and G, of course. Interchanging the order doesn't make any difference. So there are 5 types of polynomials. The first type of polynomials look like x to the power q and this product afterwards. The second type is x squared and alpha x squared plus beta times vx squared, where here alpha beta are non-zero rational numbers, and the third types of and fourth type of pairs are defined using the Dixon polynomials. And finally, there is the fifth pair where there are not many restrictions on the parameters. So these are the possibilities. Since this is a very concise and precise description of all the situations, and there might be infinitely many solutions, the Biot theorem became a widely used tool for proving finiteness of number of solutions in the case of Diophantine equations. I cannot list all or nearly all or not even all the important results where the Biot theorem has been used, but I just show a few instances of the use of them, maybe some of which I knew without searching for them. So Peter, Pinter, and Schinzel, and later Schinzel alone, applied Biot theorem for separable equations in trinomials. Stoll-Tichy investigated the problem for general Meixner and Kraftschuk polynomials. Bilu, Brinzok, Inscherhofer, Pinter, and Tichy used it for Bernoulli polynomials. Kreshow for lacunary polynomials, Dubiskat and Kreshow for truncated binomial powers, Rakowski for polynomial values of power sums, and Kulkarni and Sari for polynomial values of products of consecutive numbers. So to start to present some results, first of all, let us define the sum of products of consecutive integers. In principle, this is a polynomial which is defined by the sum of the product of terms like x plus j. So if we start to look at the first such polynomial, f0 of x, that's nothing else, just x. F1 of x is x plus x times x plus 1. F2 of x will be x plus x times x plus 1 plus x times x plus 1 times x plus 2, and so on. So in principle, what is clear from the definition is nothing else that f of x is a monic polynomial, clearly. Then it has positive integer coefficients. Its degree is k plus 1. And well, as we see, it is also visible from this that 0 and -2 will be always the root of this polynomial. These polynomials first were introduced, as far as I know, by Hajdú, Lajström, and Tengely, who proved that the Diophantine, who considered the Diophantine equation fk of x equals y to the n, and they proved effective finiteness result for that. They even solved completely the equation when 1 smaller or equal to k, smaller or equal to n. And to do so, they needed a few more involved properties of these polynomials. So about the fk of x, here are the first few polynomials, and if k is larger or equal to 3, then all the roots of the polynomial fk of x are real and simple. So the only case when there is a double root is here in f2 of x. 0 is always a root and -2 is always a root of the polynomial. And a more precise description of the root structure of fk of x is here. These are the intervals where fk of x does have a root. So in principle, each root can be put in an interval of at length at most, well, 1.5, but generally 1. So it is very well described where are the roots of this polynomial. Okay, so for our generalization of the result of Hojdula and Tengely, we needed some properties of the polynomials fk of x plus 1 and fk derivative of x. Sorry, from here the k is missing. So if k is larger or equal to 3, then all the roots of fk of x plus 1 are real and simple. That's one property which we will use later. -1 is always a root of the polynomial fk of x plus 1 for all k larger or equal to 2. Again, for k larger or equal to 2, we can describe where the roots of this polynomial fk x plus 1 reside. One of them is in the interval -k minus 1 minus k, the next one in -k minus k plus 1, and so on, up to -3 minus 2, and finally there is one root in the interval -0.50. So for k larger or equal to 3, if we consider the derivative of such a polynomial, then we can denote the roots by alpha 1, alpha 2, and so on. All these roots are real and simple, so it will have exactly k roots. If k is larger or equal to 6, then we can prove that fk derivative is 0 is positive, fk derivative in the value -1 gives a negative value, and so on. And for k larger or equal to 13, we just have fk alpha 1 is larger than fk alpha 3 is larger than fk alpha 5, and fk of alpha 2 is larger than fk of alpha 4. These are properties which we needed in the proofs of our results. Among the first results, I will mention that fk of x is indecomposable. So let us see what we mean by a polynomial being indecomposable. By a decomposition of a polynomial f of x over a field k, we mean that it is written as a composite function of two polynomial functions. So it is of the form g1 of g2 of x, where g1 and g2 are both polynomials over the same field. And we say that such a decomposition is non-trivial if the degree of both these polynomial g1 and g2 is larger than 1. So if none of the polynomials g1 and g2 is linear. If we have two decompositions, we say that these decompositions are equivalent if there exists a linear polynomial with coefficients in the field k such that g1 can be expressed by h1 in the variable lx, and h2 of x is L of g2 of x. We will say that the polynomial f of x is decomposable over k if it has at least one non-trivial decomposition. Otherwise, it is called indecomposable. And what we proved together with Basho, Hajdu, and Luca was that the polynomial fk of x is indecomposable over the complex field for any k larger or equal to 0. To prove this, we had two very nice tools, two lemmas of Dujela and Gusic. They proved that if fx is a polynomial with integer coefficients, which is monic, and it is decomposable over the complex field, then there exists also decomposition over z. Further, they also proved that if we have a polynomial f of x, which is monic and has integer coefficients, then in the case of any decomposition, f of x equals gh of x, the outer polynomial, the degree of the outer polynomial is such that its degree is smaller or equal to the GCD of the second coefficient and the degree of the polynomial. So whenever we have a decomposition, the outer polynomial is of degree less than the GCD of this coefficient and n, the degree of the polynomial. This means that the GCD of a and n, if this is co-prime, then m is smaller or equal to 1. That means that if a and n are co-prime, then any decomposition is with degree of g equals 1, which means that f is indecomposable. So any decomposition would be a trivial decomposition. So let us see how can we use this for proving that fk of x is indecomposable. First of all, let us see how fk of x looks like. We know that fk of x has degree k plus 1. It is monic. So we just denote its coefficient by 1 ck minus 1, and so on, c1. And we know that 0 is a root of fk of x, so c0 must be 0. It is not very hard. I would say it is very easy to compute ck, which is 1 plus k times k plus 1 over 2. Now, if we take a look at it, this, when k is even, then this is k plus 1 times an integer. If I add 1, that is co-prime to k plus 1. So in this case, by the theorem of Dujela and Gusic, fk of x is indecomposable. This is the easy case. When k is odd, then we have to do a little bit more of computations. In this case, we see that k plus 1 and ck has a GCD which is at most 2. Well, of course, in the case when the degree of the outer polynomial, if fk of x equals h of g of x, if the degree of the outer polynomial is 1, that's a trivial decomposition, so it doesn't count. So the only way we may have a non-trivial decomposition is that degree of h is 2, because the degree of the outer polynomial, of the external polynomial, must be smaller or equal to 2. So assume that we have a quadratic polynomial, h equals ax squared plus bx plus c. Now then, h of g of x looks like this. And clearly now, this is a decomposition of the polynomial fk of x. But by the theorem of Dujela and Gusic, we know that if it has a decomposition over the complex numbers, it has a decomposition over the integers. So we may assume, without loss of generality, that a, b, c are integers, and g is a polynomial with integer coefficients. From this, it is easy to see that a must be equal to 1, because f has leading coefficient 1. So this means that a times the square of the leading coefficient of g must be 1. All are integers, so a must be 1. This means that if u and v are the polynomial are the roots of the polynomial h, the quadratic polynomial ax squared, or now x squared plus b x plus c, then fk of x can be written like g of x minus u times g of x minus v. But we know that fk of 0 is 0. So either one or the other factor must be 0. So we get g0 equals u or g0 equals v, which now shows that either u or v is integer. But now we have a quadratic equation. If one of the roots is integer, then the other one must be integer. So both u and v are integers. So we may just denote gx minus u by h. And then we know that gx minus v will be h of x plus d, where d is u minus v. But what is important, that this d is an integer. So now we have fk of x equals h times h plus d. And let us use the property of fk of x, that fk of minus 1 is minus 1. That means that h of minus 1 times h of minus 1 plus d, they give minus 1. So since h of x and h of x plus d are integers, then h of minus 1 equals plus or minus 1, and h of minus 1 plus d equals plus or minus 1. Consequently, we obtain d equals 0, or d equals plus or minus 2. But d equals 0 would mean that fk of x is h of x to d squared. But this contradicts that all the roots of fk of x are simple roots. And when we have d equals plus or minus 2, then we get that fk of x plus 1 will be a square. But again, we have proved that fk of x plus 1 has only simple roots, which gives again a contradiction. So altogether, fk of x is indecomposable. This theorem was used to prove the second part of the following more general result. Let g of x be a polynomial with rational coefficients, and consider the Diophantine equation fk of x equals g of y. So now the right-hand side is an arbitrary polynomial, and on the left-hand side we do have this polynomial, which is the sum of products of consecutive integers. Assume that k is larger or equal to 3. Then in the case when the degree of the polynomial g is 0 or 2, then there exists an effectively computable constant depending only on this index k and the polynomial g, such that the maximum absolute value of the integer solutions of equation 4 is bounded by this constant. So we can prove an effective finiteness theorem in this case. Whenever the degree of g is larger or equal to 3, then we can prove that equation 4 has only finitely many integer solution, unless we have g of x equals fk h of x. Clearly, in this case, there will be infinitely many solutions. So, in the case of g equals 0 or 2, we have effective finiteness, and in the case of g larger or equal to 3, we do have ineffective finiteness. Here in the second point, the finiteness is ineffective because we are using the Biluty criterion, the Biluty theorem. And since the Biluty theorem is ineffective, the results proved by it will also be an effective result. This means that there are no bounds on the size of the solutions. It proves a finiteness where there is no guarantee that there is a bound. We cannot just produce an effective upper bound. What about the cases which are excluded? first of all, whenever g of x equals fk of h of x, then clearly we may have infinitely many solutions. Also, when degree of g equals 1, we may have infinitely many solutions. Well, it is clear whenever g is linear, then this might have infinitely many solutions. Let's say if g of y equals y, then we just have fk of x equals an integer, and if y is that integer, that's a solution. So for every x, we get a solution y. Again, when g of x is fk of h of x, the same situation holds. Whenever h of x assumes a value, then we can take for, let's say for y, or for the other unknown, this value, and we get a solution. So in these cases, we always have infinitely many solutions. And it may happen also for k smaller or equal to 2. At the beginning of the theorem, we assume k is larger or equal to 3. Well, when k is smaller or equal to 2, it may happen that there are infinitely many solutions. These conditions are necessary in case of our theorem. Now, a few words about the proof of statement 2. I will not tell anything about the proof of the first statement, but about the second statement, where we use the Biluti theorem, I would like to sketch the main ideas of the proof. So it is this part of the theorem. So, as in the theorem, we assume that k is larger or equal to 3, and the g is a polynomial with rational coefficients of degree at least 3. And we assume that this equation has infinitely many solutions. Now let us see what can we infer from that. The Biluti theorem describes very explicitly in what situation this can happen. Fk of x must be phi of f of lambda of x, and g must be phi of g of k of x. The phi here is the same polynomial. Lambda and kappa, they are linear polynomials. And f and g are coming from a standard pair over Q. Now, we have proved a few slides before that fk of x is indecomposable. So that means that the degree of this phi is either 1 or it is k plus 1. If it's 1, then of course f must be of degree k plus 1. Otherwise, f will be linear. So let us see the two cases. We will address first the case when degree of phi of x equals k plus 1. We just recall that this is how fk and g of x are composed. Now, from this composition, we see that the degree of f must be 1. Because this is of degree k plus 1, phi is of degree k plus 1, so f must be linear. But then, clearly, we have fk of x equals phi t of x, where t of x is f lambda of x. It's linear. Now we can take the inverse function of the polynomial function t of x, so that t of t minus 1 gives the identity function. So this means that fk of t minus x is just phi of x. So we can express phi of x in the form fk of something which is linear. Now, if we go to the other part of the other polynomial g of x is composed like phi of g of kappa of x, but phi can be written like fk of t minus 1. And now you see that this is fk of something. And in principle, we don't care what is here inside. The only important feature is that it is a polynomial with rational coefficients and of degree at least 1. So this means that we can prove that g of x equals fk of h of x. This is the exceptional case when we may have infinitely many solutions. And we will see that there are no other possibilities for infinitely many solutions, since the other possibility is when the degree of phi of x equals 1. Whenever the degree of phi of x equals 1, we can write phi of x like this. And in this case, we have to study all the possible standard pairs. Now, we have 5 kinds of standard pairs. In the case of standard pairs of type 2, this can be excluded because there we have a polynomial of degree 2. But f of x and g of x cannot be of degree 2 in this case, because f of x must be of degree k plus 1. If I go back here, now phi is linear, lambda is linear. So in order to get a polynomial of degree k plus 1, f must be of degree k plus 1. It cannot be a quadratic polynomial. So on the other hand, the other polynomial, let me just come back for a second here to the second type standard pairs. So one of them must be x squared, and the other one must be of this shape. But here it's clear that this polynomial has multiple roots whenever the degree is larger than 2, or larger or equal to 4. Sorry. So in that case, again, we see that it has multiple roots, but fk of x cannot have multiple roots. So this way we can exclude polynomials of pairs of polynomials of type 2, standard pairs of type 2. Standard pairs of third and fourth kind, they are the polynomials which are defined using Dixon polynomials. We can exclude them by comparing coefficients in this equation. In the case of standard pairs of type 5, in principle, we have 2 cases. Fk of x must be either of this shape, which contradicts with the indecomposability of f. If we look at this, then this shows that there is a polynomial a times lambda x squared minus 1 to the cube. But this means that this polynomial is composed to phi x cubed plus phi 1 x cubed plus phi 0. So this is a non-trivial composition of polynomials. Fk cannot be of this shape. On the other hand, we may have fk of x equals this shape. And in this case, we just compare again coefficients. And after comparing 3-4 coefficients, we get a contradiction. In the case of the first type, again, the root structure of fk of x and the derivative of fk of x prove that such standard pairs are impossible. Well, of course, here we have some lengthier computation, which I have no time to show for these situations. But this is the flavor of the proof. We also proved an effective result. In the case of the equation fk of x equals ay to the n plus b, we could prove that the solutions are bounded by an effectively computable constant. Well, this is a generalization of the result of Hoydul, Leishram, and Tengay, who considered the case a equals 1 and b equals 0. Now we will switch our attention to a different topic. Komornik polynomials are polynomials introduced by Vilmos Komornik for some results concerning digital expansions. If we define a sub n of x equals x to the power 2 times 3 to the power n minus x to the power 3 to the n minus 1, and we multiply such polynomials from k equals 0 to n, then we get the nth Komornik polynomial. Komornik polynomials, the first few of them look like this. The first one is easy to see, but the second one and the third one are these polynomials. So we can see that these are polynomials with coefficients plus or minus 1, and there are the degree of such polynomials is always 3 to the power n plus 1 minus 1. All coefficients are plus or minus 1. Below the highest degree term, below the main term, there are no other coefficients than plus or minus 1, including 0. There is no 0 coefficient, so all the terms are present. It consists of 3 to the power n plus 1 monomials, and all these monomials have coefficients either plus 1 or minus 1. It is also proved that all the complex roots of such polynomials are simple. The first important result concerning Komornik polynomials is that Komornik polynomials are incomposable over C. And this helps us to use this to apply the Biluti theorem later. But for the moment, let us see a few more properties of A k of x. In principle, there is a polynomial identity AL plus k of x equals A sub L of x to the power 3 to the power k. And if we denote the Fibonacci numbers by phi 0, phi 1, and so on, and we define R sub k to be phi of 3 to the power k plus 1 plus phi of 3 to the k minus 1 minus 1, then these are clearly integer numbers. These integer numbers will play an important role in the GCD of two values of this polynomial ak of x. So if we take the polynomial ak of x in any integer place, and we compute it for the index L and for the index L plus k, then the GCD of these two integers will divide the integer R sub k defined just here using the Fibonacci numbers. So this way, for polynomials with index close to each other, we can compute the GCD, or we can prove how much is the GCD. If they are consecutive indices k and k plus 1, then the GCD will always be 1. And if between the indices the difference is 2, then the GCD is either 1 or 5. So after these auxiliary properties, let us show the results concerning Diophantine equations containing Komornik polynomials. The problem originates from Attila Pető, who asked in a conference about the finiteness of number of solution of P sub n of x equals P sub n m of y. With Kolus, Pink, and Szustek, we did prove that the equation P sub n of x equals P sub m of y has always finitely many integer solutions. And even more general, we consider the equation with arbitrary right-hand side. And we did prove that if g of x is not of the form P sub n of h of x, or g of x is not of the form gamma of delta x to the L, where gamma and delta are linear polynomials with rational coefficients, and L is just the degree of this polynomial g, then we have only finitely many solutions. However, I have to mention that the first exception that's necessary. The second exception, we couldn't prove that in this case there are infinitely many solutions. So it probably may be excluded, but we were just unable to prove that. Well, that was what it was written here, and of course, since we use Biluti's theorem, the result is ineffective. We also did prove some results concerning this polynomial which are effective. In the case of the equation P of n of x equals y to the m, we did get effective solutions both in the case m equals 2 or m larger or equal to 3, and we even could prove an effective result for the exponent m from here whenever y is different of plus or minus 1. And for the concrete cases of y square in the right-hand side, we did solve completely this equation. There are some trivial solutions, and except of the trivial solutions, it exists only one non-trivial solution in the case when n equals 2, and we did solve the equation also for n equals 1, 2, 3, 4, and 5. Further, we did prove, we did solve completely the equation P of n of x equals y cubed for n equals 0, 1, 2, and 3. As my time is going, I will not tell about these results in details. However, I will switch to my third topic, power values of power sums. Well, if we take sk of x, 1 to the k plus 2 to the k plus x to the k, this is sk of x, and the problem sk of x equals y to the n. This is a well-known and much investigated classical problem. It goes back to Luca Watson, and the first internationally known breakthrough was due to Scheffer, who did prove that if k and n is not one of these pairs, then this equation 16 has only finitely many solutions. He also conjectured that if Kn is not of this pair, not one of these pairs, then the only non-trivial solution is given by 2, 2, 24, and 70. Many results concerning this equation have been established during the last few decades. Gyuri, Tiedemann, and Forhoof proved an effective version of Scheffer, and they have another extra feature that also n was an unknown. So in this equation, also the exponent was an unknown for them, and the effective finiteness was working also in this more general case. Then Pinter proved that for non-trivial solutions, we have this bound. The conjecture was verified by Jacobson, Pinter, and Walsh for some bounded values of k and n equals 2. Bennett, Gyuri, and Pinter extended the result to 1 smaller or equal to k, smaller or equal to 11, and arbitrary n larger or equal to 2. This was again an important breakthrough. And Pinter verified the conjecture for n larger than 4 and 1 smaller or equal to k, smaller than 170. This is, of course, not a complete list of results. However, Hoydu initiated the investigation of this equation for fixed values of x. For values of x which are smaller than 25 and are congruent of 0 and 3 mod 4, he computed all the solutions, and together with Hoydu, Miyazaki, and Pink, we extended this result for the cases when k is congruent to 1 or 2 mod 4. In principle, this shows that we proved the Scheffer conjecture for x smaller than 25 and n larger or equal to 3. Now, finally, I would like to mention a few other kinds of equations where sk of x is included and the Biluti's theorem is used, but these results are not mine. I couldn't contribute to this topic. Bilou, Brinzo, Kirchenhofer, Pinter, and Tichy, they considered the equation sk of x equals Sm of y. And for the case when g of y is the product of consecutive integers, Bilou, Brinza, Kirchenhofer, Pinter, and Tichy proved again. Then Gyuri, Kovács, Péter, and Pinter for binomial coefficients, and for this kind of sums, Gyuri, Kovács, Péter, and Pinter. So also for such kind of separable equations, the Bilou-Tichy theorem was used, and it was a powerful tool. Thank you very much for your attention. This was what I wanted to tell.
Yeah, so thank you very much, Attila, for your very nice and rich talk. So it's open for discussion, and I already can see a very precise question by Gary Walsh, who is our next speaker. So the question you can read here, is it possible to read it?
Just a second, I'm trying to
So
find
he is asking, where do the upper bounds come on page 28?
On page
very precise question.
Page 28, just let me find, oh no, it's 30 now? No, it's 20, oh. It's
yeah, 28.
Oh, I see. Well, these are coming from super and hyperelliptic equations from Baker's theory, from a result of Jan-Henrik Evertse, Kálmán Győri, and myself. We have a completely explicit result for this case, and we use that theorem for this.
Okay, so thanks to you from Gary. Are there other questions, remarks, comments? So it's nice that you could answer the question of Attila Pető on the Komornik polynomials. That's really very nice.
Thank you very much. Well, we were happy to be able to answer it, yes. But it's more or less due to you and Bilou.
No. So you have to check.
The
yes.
powerful tool was offered by you.
Other questions, remarks, comments? No, then thank you very much again for your talk.
Thank you very much.
And hopefully see you in Debrecen next year. So
yes, hopefully see you in Debrecen, yes.
Yes, hopefully that next year is better than this year. So Gary Walsh already is here. So we have a break of 10 minutes, and then we have the pleasure to listen to his talk. So see you in 10 minutes. introduce our next speaker, Gary Walsh from Ottawa, and you can read the title on binary quadratic two equations and related topics. Please, Gary.
Well, thank you to Robert and all of the organizers, of course, for giving me a chance to speak today. This is a great pleasure. Of course, I would much prefer to be in Marseille, but we all would, I'm sure. But this is a nice way to get together given the circumstance. And I also, since I have my colleagues from Debrecen here, I want to say hello and thank them also for the years of collaboration and inspiration they've given to me. I took a little bit of a break from research for a few years, being a father. So in the last 2 years, I've returned to doing research, and I'm learning a lot from this conference and from other conferences over the last 2 years, and have a few things going on research-wise that I'm going to talk a little bit about today. I had some interesting conversations with Paul Voutier and Michael Bennett and Andrew Granville, and so there's a lot of interesting mathematics going on that I'm trying to contribute to. I feel bad for Mike Bennett right now. He's dealing with a fiasco at his university, so I wish him well if he's anywhere in touch of this. But I just wanted to mention that I really hope that, you know, some aspect of this talk will be of interest. A lot of it is not very highbrow. It's very hands-on. I'm trying to solve Diophantine equations in various ways. And so I hope this talk will be of interest. Let me move along to the next slide and mention that some of this work, or most of it, is joint work with Michael Bennett. And at the end of my talk, I will talk about something which is joint work with Pingzi Yuan from the People's Republic of China. So in this talk, I'm going to talk about index form equations. They come up in a very natural way when one is trying to compute power integral bases of number fields. This is a very large subject. We're not going to cover this entire subject. We'll be very interested in one particular area of research in this topic. In particular, what I want to look at are pure quartic fields. And when trying to compute power integral bases of pure quartic fields, a family of two-way equations come up. And so what we're trying to do is completely solve this family of two-way equations. And in particular, what we're able to do is provide a different approach to solving this family of two-way equations than the methods that have been given in the past. So that will be the main thrust of the lecture, this part. But since there are other things to say about this problem, I will continue and talk a little bit about how it is very closely connected to the ABC conjecture. Eventually, I will talk about a related family of elliptic curves, like I said earlier. And this last part of the talk is joint work with Pingzi Yuan. Okay, so without further delay, let me start off by looking at the source of index form equations or index forms. Where did these things come from? Well, let's look at an integral basis of a number field K, and I'll just write it as 1 omega 2 up to omega of n. And I'm going to look at the linear form on the n-1 variables capital X sub 2 up to capital X sub n. And I'll write that as a vector. So we're looking at the linear form L evaluated at the coefficient or the vector of variables x2 up to xn. This the discriminant of this linear form from the number field K down to Q is defined in the obvious way. You look over the automorphisms of, or the embeddings of K into the complex numbers. You look at all the possible differences and square them. So this is the standard definition. And if you do that, what you end up with is a polynomial I of x to the power 2 times the discriminant of the field. And this I of x is the polynomial that we're trying to get our hands on. It's a decomposable form with integer coefficients, and it's obviously of degree n times n minus 1 over 2, where n is the degree of the number field K, and this is called an index form. In particular, let's look at what this index form gives you. It gives you a measure of how far away a number will generate a basis of the field. So let's take some gamma in the field K and write it out in the basis x1 plus x2 omega 2 and so on. Then if this element is a primitive element, so if it generates the field, then the value of the index form at gamma is, well, how do you evaluate it? You evaluate it using the coefficients. We're doing it with respect to the basis, so this is what we do. And this number in absolute value is the additive index of the ring generated by gamma inside the additive group of the ring of integers. So in particular, if this number is equal to 1, if we're able to generate the entire ring of integers, then in a way this number gamma is quite special, and very special, and we call powers of gamma a power integral basis. So 1 gamma, gamma squared up to gamma to the n minus 1 is a power integral basis precisely when that index is equal to plus or minus 1. And the problem for a given number field is to find values x2 up to x sub n which solve this equation. And in general, this is obviously going to be a very difficult problem. So let's take a toy example. Q adjoin the 4th root of 2. And well, we'll start with a basis in order to get going. So I'm cheating a little bit, but I'll come back to this basis in a second. So here I'm going to take the obvious basis 1 alpha squared and alpha cubed. And with that basis, when you go through the process of computing the discriminant and looking at the index form that comes out of it, what you get is this polynomial of degree 6 in 3 variables x2, x3, and x4. So a priori, in advance of knowing anything, if we need to compute a power integral basis of this simple quartic field, then we would need to solve the problem of this polynomial equal to plus or minus 1. Now, solving a degree 6 polynomial equation in 3 variables like that sounds like a pretty difficult problem. So, so solving this equation, I evaluated x2, x3, x4 equal to plus or minus 1. Non-trivially is obviously a very difficult problem. So trivially, we can solve it if we set x3 and x4 equal to 0. Then we have x2 equal to plus or minus 1, which gives us the trivial basis here. Okay, but we want to know if there are other power integral bases other than the trivial one. So in general, if I replace the number 2 by any positive integer or any fourth power free integer or a square free integer, how are we going to go about solving the equation I of x equal to plus or minus 1? So the way to get around this difficulty comes from a beautiful lemma by three people, Istvan Gal, Attila Petto, and Michael Post, proved in 1993 the following fundamental result, which appears in many papers and is extremely useful for this purpose. So let me start by giving the setup of this lemma. There's a lot on this slide, so I want to just present it a little bit at a time. So here we have a quartic number field, Q adjoins psi, and the polynomial is some generic quartic polynomial. And I is the index that we defined earlier with respect to this basis 1 psi, psi squared, and psi cubed. N will be the value of I at psi, and M will be the minimal positive value of the index over integer inputs to I. Then we are going to need the cubic resolvent of the polynomial f sub psi, and I'll just write it as capital F of uv, which I can write in terms of A1, A2, A3, and A4 as follows. I won't read that off. And also in this lemma, there are two associated polynomials, Q1 and Q2, in three variables, x, y, and z. Again, those polynomials are defined completely in terms of the coefficient of f sub psi. And with all of this in place, we get the beautiful result below. So if you have some integer phi in the field, now capital D will denote the denominator of phi. So here phi will generate a power integral basis. If it does, then there is an integral solution uv of f of uv equal to plus or minus this denominator of phi to the power 6 times little m times little n, where u and v are given explicitly by the polynomials q sub 1 and q sub 2. So we use this lemma to go from where we were on the previous slide, almost in a hopeless situation, to now we're having to solve a 2e equation, basically. So we can do this computationally. And what I'm interested in specifically are pure quartic fields. So if I look at the field x to the 4th minus d, defined by the polynomial x to the 4th minus d, here psi is going to be the root d to the 1/4. Then this, as I showed earlier, because of the trivial solution to the very complicated equation of degree 6, we get that this is an integral basis precisely for d bigger than 1 in absolute value and d congruent to 2 or 3 mod 4. This comes from some work of someone else, another group that I'll mention in a second. But let me get to the main point here, that now, because of all of the other coefficients being equal to 0, the polynomial f that I defined on the previous slide becomes considerably simpler. In particular, it's simply u times u squared plus 4dv squared. And the other polynomials, q1 and q2, also become extremely simple. U is given specifically by x squared minus dz squared, and the value v is given by y squared minus xz. So that's a simple computation to get that. So what does that say? Well, if we go to the lemma, it says that our phi if this generates a power integral basis, then D is equal to 1, the denominator. The values of M and N are also equal to plus or minus 1. So by the lemma, that gives the value of the 2e equation being equal to plus or minus 1. And if you look carefully at this, here I really want D to be bigger than 1. So I put in absolute value by mistake there. So here D is positive. We have a positive definite form. And the only way you're going to get plus or minus 1 on the right-hand side is if this value, these are both plus or minus 1. And of course, that implies that V is equal to 0 right here. So you get that U is equal to plus or minus 1 and V is equal to 0. So this really nails down the possible values. So here, this is what I've written. U, which we know is x squared minus dz squared equal to plus or minus 1. V, which is y squared minus xz, is equal to 0. Now, this equation right here, x and z are co-prime from this equation. So that says that these are both squares. So what I'm going to do is label little x to be capital X squared. And I'm going to label little z to be capital Z squared. And I'm going to plug those into this equation right here. And at the end of all of this analysis, what we get is this quartic equation. So this is really going to become the main topic of the lecture, is this quartic equation right here. So what we have is, if you have a power integral basis generated by phi, it really has to look like x squared d to the 1/4 plus or minus xz d to the 2/4 plus z squared d to the 3/4, where x and z come from a solution of this quartic equation. So for example, so this is the result I mentioned briefly earlier. It was a result of Ahmad, Hamid, Husneen, and Nakahara from 2011, and they showed that for arbitrary d congruent to 2 or 3 mod 4, then you always get an integral basis from the trivial solution of the index form equation. So this set of numbers is a power integral basis. So this is kind of the trivial solution to our problem, but there are non-trivial solutions to the problem. So for example, if we look at d equals to 15, we go to our quartic equation right here, we see that there's a solution with x equal to 2 and z equal to 1. And so we can just write down a generator of a power integral basis using the values x and z. So there it is. So it becomes a very simple process to find these non-trivial generators of power integral bases using the lemma of Gall, Peto, and Post for this family of fields. So this has been worked on by a few people. Let me talk about some computational results that have appeared in the literature on this problem. There's some really nice work by Attila Berthes, and I don't know the fellow Basso, and Kalmanjiri and Akos Pinter in 2010. They were able to completely solve this 2 equation for d up to 400. And in the same work, they were able to solve it for d up to 2000, provided d is odd. And I should mention that in this paper, their work is not specific to the case of degree 4, the equations of degree 4. They prove results for all n using modularity of elliptic curves and Frey curve methods, and it's a very, very deep paper. I'm only talking about the work they did to deal with the degree 4 case here. So one should keep that in mind. That wasn't the focus of their work. This was picked up again by Istvan Gall and Laszlo Remete, and they were able to find all small solutions in a very efficient manner for D all the way up to 10 to the 7. And I'll just say a few words about the computations that were done. My understanding is that the 2010 computations used a combination of magma and, Paris for solving TUI equations. And I think most of us at the conference are well aware of solving TUI equations with large coefficients becomes very onerous. It's very time consuming. The bounds from linear forms and logs can be very large. Computing units in quartic fields becomes very labor intensive, and so on. And you know, the L cube reduction process might not give you a small enough bound, so your exhaustion may be over a very large space. So that this was probably quite a bit of work to do this. And similarly in 2018, I believe they used cache on a high performance computer, and the algebraic numbers that came up in the computation had thousands of digits and required quite a bit of computation to get that work done. Okay, let me get to what I want to talk about. My contribution, or with Mike, is we looked at this paper of Istvan Gall, this beautiful paper, but we had an idea that came from an observation. So the observation is as simple as you can get. It's if you have integers x and y satisfying this quartic equation, then x squared plus y squared is a unit in this ring of integers, obviously. So, well, what does that give you? It surprisingly a lot. So let me just mention quickly some more in the way of some observations we made early on in the process. So here, epsilon sub d will denote the fundamental unit in the ring z adjoin the square root of d. And I'm going to list off some d for which this equation is solvable. So here, the first one is 2, and the solutions are 1 and 1, x and y both equal to 1, which gives you the unit 1 plus root 2. And lo and behold, it's the fundamental unit of the quadratic field. Okay, well, maybe that always happens. Maybe it's always the fundamental unit. Who knows? It's just a question. And the second example is 3 squared plus 2 squared times the square root of 5. And well, no, it's the square of the fundamental unit. So maybe this isn't true. Well, let's look a little further. And if we look at 15 and 39, in those cases, we get the fundamental unit. So there seems to be a possibility that whenever you have a unit of this form, or whenever you have a solution to this TUI equation, you're really looking at the fundamental unit in this ring. Well, we did more computation with the table from the paper of Gall and Remete, and for all cases different than 5, it turned out that the unit that one gets from the solution of the quartic TUI equation does in fact give you the fundamental unit in the ring z adjoin the square root of d. So, okay, maybe we ought to try to prove this thing. And in doing so, it turned out to be a pretty straightforward thing to do. So here is the theorem that I want to state. So if d is a non-square positive integer, and assume there exists x and y satisfying this quartic equation, then in fact x squared plus y squared root d is the fundamental unit in the ring z adjoin the square root of d, except for d equal to 5, in which case we just saw that it's the square of the fundamental unit. And the proof is very simple given the tools at our disposal. So in order to prove this, we use two beautiful theorems of Wilhelm Ljunggren and another beautiful theorem by Chen and Voutier. Let me just run through that rather quickly. So the proof of the theorem uses this amazing result of Ljunggren from 1942. I've mentioned this in several papers, and I'm probably his biggest fan. So these theorems should never be forgotten. So I'll just state them one more time. So D here is a positive non-square integer. Epsilon sub D is the fundamental solution of the Pell equation, x squared minus dy squared equal to 1. And for k bigger than or equal to 1, I'm going to represent the kth power of the fundamental unit or fundamental solution as t sub k plus u sub k root d. So you get two sequences, t sub k and u sub k, generated by taking powers of this unit. And what Ljunggren actually proves, he doesn't state it this way, but what he actually proves is there's at most one odd index k for which t sub k is a square. There's at most one index congruent to 2 mod 4 for which t sub k is a square, and there are no indices congruent to 0 mod 4 for which t sub k is a square. That's actually how the proof works, what it gives, and which is, it's surprising to me how much work went into this. The proof is very complicated, it's very long, it's very sophisticated. It used Skolom's method. It's hard to follow this work unless you really, you know, get your hands dirty and follow this. And it's surprising to me, the natural question that comes up when one reads this theorem is, okay, which value of k? So if there's only one odd value of k, then which value of k is it? And one would immediately think, would it be k equals to 1? And if you do just a little bit of computation, you really don't need a computer at all. So Ljunggren could have asked this question and could have tried to prove it. It's surprising that he didn't prove it himself, that k would be equal to 1. Similarly, the same proof you think would work for k equals to 2. In any event, this was proved many years later by John Cohn. So I will just state it as a lemma. So if k is odd and t sub k is a square, then k equals to 1. And similarly, if k is congruent to 2 mod 4 and t sub k is a square, then k is equal to 2. And the proof uses a very clever manipulation of Legendre symbols. And it just surprises me that Ljunggren didn't try to prove this himself or even make any mention of it whatsoever in his papers. Okay, let's go back to the proof of our theorem. It's pretty straightforward. If we have a unit which is of the form x squared plus y squared root d, and let's suppose the index is not equal to 1, then by Cohn's refinement of Ljunggren's theorem, we have k equals to 2. Wow, okay, we're pretty close already without doing anything. Now, if k is equal to 2, then we have that this number y squared is u sub 2, and u sub 2 we know we can write from properties of solutions of Pell equations. We can write it as 2 times t sub 1 times u sub 1. So that says that since these numbers are co-prime, t sub 1 is either a square or twice a square. So I'm just writing it as either a square or twice a square when I do that. And furthermore, because of the identity t sub 2 equal to 2 times t sub 1 squared minus 1, we get that the number x squared, which is t sub 2, is either 2r squared minus 1 or 8r squared minus 1. And both of these cases can be dealt with basically one swing at the bat using Ljunggren's famous result on x squared minus 2y to the 4th equal to minus 1. Everyone knows about this, I'm sure. And by applying this result, it actually, we work things back, and the only value of D which we get is 1785. And in that case, the only solution to this equation occurs at k equal to 1. Okay, so this completely solves the problem in the case of the norm being 1. Now, if the norm is equal to -1, we have, this is an easier case because it's a straightforward consequence of a very beautiful theorem by Chen and Voutier from 1997, who generalized the result of Ljunggren that I just mentioned. And here, D bigger than 2, so I should say that D is bigger than 2, be a non-square positive integer for which the negative Pell equation is solvable. And I'm going to let xy equal to tu denote the minimal solution of this equation. Then the quartic equation x squared minus dy to the fourth equal to -1 has at most one solution in positive integers, and if it exists, it comes from the minimal solution. It's actually equal to it. Okay, so they really solved this problem completely. It's a beautiful result, and that gives the proof of our theorem in the case of -1. So we really had nothing to prove. It was a straightforward consequence of results that appear in the literature. Anyway, going back to computing power integral bases by this theorem that we've just stated, determining those values of D for which a non-trivial power integral basis exists, or in other words, when this quartic equation is solvable, we don't need to solve quartic 2 equations. We just need to compute fundamental units in these quadratic orders. Okay, well, I could go ahead and start computing this, and of course I could get a little bit further than 10 to the 7, but there are people who actually make a living doing this kind of computation. So rather than do this ourselves, we've deferred to the champions of this kind of work. And right now, at this very moment, as we speak, CPUs are busy all over Canada computing fundamental units in quadratic fields. And I'm not kidding. This computation should be done in the early new year. This was promised to me by Michael Jacobson. So they have a program underway that will compute a table of fundamental units of quadratic fields for all D up to 2 to the 40. So that's like about 10 to the 12th. So once that list is completed, Mike Jacobson said he would do a favor for us and go through his list and give us all the values of D for which this equation is solvable. So we should get notification of a complete table up to 2 to the 40 sometime in the new year. Well, okay, so as promised, I mentioned that there was a connection to the ABC conjecture. Now, the ABC conjecture goes back to the mid-80s. Joseph Oosterlee first proposed a formulation and later refined by David Masser. And the way I like to read the ABC might be a little bit different than what is standard. I just think this way is more intuitive. So this phrasing of the ABC says that for any epsilon bigger than 0, there are only finitely many triples of coprime integers A, B, and C, satisfying A plus B equal to C, for which C is bigger than the radical of ABC to the power 1 plus epsilon. So the quality of a triple is given specifically by this L of ABC, which is basically all I'm doing is isolating the exponent. So it's log of C over log of a radical of C. I don't know where this number L comes from. It's a bit of a mystery to me. Any event, there's some rather difficult discussions going on around the world concerning the ABC conjecture. As we all know, there's this work going on in Kyoto, and a friend of mine described this unfortunate situation that inside Kyoto, the ABC conjecture is true. In fact, an effective version of the ABC conjecture is true inside Kyoto, and outside Kyoto, it's not true yet. So everyone can decide for themselves. I believe those that have won Fields medals, so I'm in the non-Kyoto side of things. In any event, we do need, for our purpose, an effective version of the ABC conjecture in order to connect with our problem. This version of the ABC conjecture is ineffective and not terribly useful. So, well, it's useful, but it's not going to completely solve the problem we'd like to be able to solve. Now, effective, let me just mention a few of the top ABC. If you've looked at ABC before, you're probably familiar with these numbers. This is from RaySat, I believe, and these are the other examples. So essentially, as you would expect, all of the numbers involved have small prime factors, and the ABC conjecture says that if you add two numbers with small prime factors, you're rarely ever going to get a number that has all small prime factors. So that's what ABC is all about. But what I said before is we really want to have an effective version of ABC, and this was proposed by Brauken a few years ago. He said that if the value of L or R, whatever the case may be, is bigger than 1.5, then all positive integers satisfying ABC with the value L bigger than 1.5 are given in the table that I just showed. So he used that effective version to prove results, Diophantine results and otherwise. But unfortunately, this conjecture is actually false. So after Brauken published his paper, there was a computation by, I can't remember the name of the person who found this particular counterexample, but in fact, it has quality bigger than 1.5 and not in the table that I just showed you. So one has to be really careful about these effective versions of the ABC conjecture. And my way of being careful is to, hold on a second now. I want to mention that there is an updated version of the tables on Bart Desmet's website. If anyone cares to look, you can just Google Desmet ABC and you will find the current version of the ABC table. My way of being careful about these is to throw caution into the wind, and I'm going to state what I call a restrictive effective ABC conjecture, and I'll describe what I mean by restricted in a second. So here, what I'm going to do instead of A, you notice there's a 1 here, so I've replaced C by B plus 1. So here's my A, B, and C. So I've taken away 1 degree of freedom. I'm only going to look at all triples of integers 1, B, and B plus 1. And what I'm going to do is I'm going to be even more ruthless than Brauken. I'm going to change 1.5 to 1.4. And this is my effective version of the ABC conjecture that I'm going to use for the problem that we're looking at. So here B is a positive integer, R is the radical of B times B plus 1. Then as long as this triple is not in Desmet's table, we always have B plus 1 smaller than the radical to the power of 1.4. So if anyone finds a counterexample to this, I'd love to see it. It could happen. I'm not saying it won't. I'm just throwing it out there for discussion, and I'm using it for my purpose. So in particular, if you have a solution to this Cordic-Tui equation and you assume the restrictive ABC conjecture, effective ABC conjecture, then in fact, the fundamental unit is really, really small. It's smaller than 2D squared. Remember, in general, fundamental unit is huge. It's e to the root d. So it has like root D, big O of root D coefficients, X and Y. So here, having a bound of 2D squared is really small. Well, what does that mean? That means that in order to compute the fundamental unit, we only need to compute a few convergents of the continued fraction expansion. And once the coefficients are bigger than 2D squared, we can break the computation. We know that there can't be a solution to this equation. So my question then about this is, given how much CPU Booker and Jacobson are using to get all the way up to 10 to the 12th, and believe me, it's a lot. If one uses our restricted effective ABC conjecture and through the same amount of CPU, how large could we solve this equation? It would be interesting to see. I don't know if there's any use in doing that, but nevertheless, it's a question. Now, using this idea, we were able to replicate the list of values of D up to 10 to the 7 in about half an hour on my laptop. So the point being that, you know, obviously this is going to be a very efficient way of finding which values of D have power integral bases. And in fact, when I said about what I said about the continued fraction expansion of the square root of D, I looked at the average number of iterations required. Some required a large number of iterations. They may have had a lot of ones in there, a lot of partial quotients, which were ones, but typically we were able to get past the 2D squared bound after 6 iterations on average. So that shows how small the computation is compared to actually having to find the fundamental unit in the quadratic field. Okay, for the last part of my talk, I will go through rather quickly because I see that I'm running out of time. There's a theorem that Pingzi Yuan and a colleague of his, Lin, and I proved, and it has to do with a question that Zagier asked a long time ago. I believe this is from a paper, Large Integer Points, from maybe 1987 or something. Yeah, 1987. And the question he asked is whether or not this large integer point is the largest integer point on this elliptic curve of relatively small height. And so first of all, one should notice that this is a very special case of this family of elliptic curves. And it's nice to look at things as polynomials sometimes, because polynomials factor, visually factor in a very, very nice way oftentimes. So here we are, we actually have a factor, x minus 2, right? So we factor this polynomial. So in other words, this family of cubic polynomials defines, they all define elliptic curves with a 2 torsion point, right? That's really what this is all about. And things oftentimes like computing the rank of a curve and other things like that become quite a bit easier. So here, I'm going to just look at my family of curves that you get after this so-called shift from x minus 2 to x. And Zagier's curve is the particular case, y squared equals x cubed plus 6x squared plus 39x. Now 39 becomes kind of a special number. So it's a previous curve is a special curve in this family. Zagier's curve is when t is equal to 3 and p is equal to 13. So this is the family of curves that I want to look at, but I need to place restrictions on t and p in order to get the result that can be proved. So the t and the p are odd primes for which t minus p over 2 is also an odd prime. And furthermore, t and p have to be different than 1 mod 8. In that case, there is at most one integral point on this curve, y squared equal to x cubed plus 2t x squared plus tpx with y bigger than 0, unless the equation x to the fourth minus tp y to the fourth equal to 1 is solvable in positive integers x, y. And if that were to happen, there may be as many as 2 solutions, but no more. And so we're back with our quartic equation once again. It rears its head. And so it seems that this condition that I stated relating to this equation only happens in the case d is equal to 39. So I'll just state that as a conjecture for anyone who cares. I can't prove it. I don't know how to prove it, but I'm sure that it's true that this equation is never solvable for 2 primes t and p satisfying the conditions of the theorem, or maybe it may not be solvable for any 2 primes other than 3 and 13. Okay. Now, the proof of this theorem, I'm really running out of time. The proof of this theorem, I'm not going to go through in detail. I'll just mention very quickly, how does one go about solving this equation at all? Well, there are various ways. Obviously, you can use programs on the computer, Magma, Cache, Paris, have the basic ideas are stored in those programs. And there's a proof that came from Chen. This is the same Chen as the Chen-Vouzier theorem. And Zhu, they solved this using p-adic analysis and algebraic number theory, which goes back to the work of Skolem. But it's complicated. And in any event, there's a different way to solve Zagier's equation. And first of all, the shift that I talked about earlier, there's a reduction step to a quartic equation. This quartic equation has many cases also, so there's a second reduction step to another quartic equation. And then finally, we can appeal to results that appeared in this talk. So, and I'll try to do that in 2 minutes. So first notice again that we have x equal 2 as a root. So we do the shift and we get the curve that I defined earlier. And so for this curve, we just factor out the x and notice that the greatest common divisor of x and the cofactor has to divide 39. So for a point other than 0, 0, we get integers u and v satisfying these 2 equations, or 3 equations, I guess. And d is one of these numbers. And out of these 8 cases, 7 of them can be dealt with using elementary methods. That's what I'm saying here, maybe modular arguments or solutions to Pell equations and so on. And the difficult one that remains after looking at those 7 cases is this quartic equation right here. So in the case of that quartic equation, the way we proceed from there is we have v squared equal to this. So we subtract the 3u squared, we eliminate it, and we get 30u to the fourth. And a few reduction steps from there, or just some manipulations, gives you many quartic equations of this form where r and s are coefficients satisfying that their product is about 120. And when you look over all those possibilities, there's really only one difficult case. All of them can be dealt with in relatively simple ways. So this one difficult case, we appeal to the fact that we can rewrite it as a Pell equation with coefficient 39. And in this case, we get that this number 2g squared has to be u sub 2t. It's the index is even for obvious reasons. And finally, what does that say? That says t sub t and u sub t are both squares. And we've seen before that when that happens, t has to be equal to 1. Okay, so what does that tell us? That this number that we had on our previous slide has to be the square of the fundamental solution. And this gives us our values, G, F, W, U, and so on, V, and finally, X and Y are the numbers that come from Zagier. So it's surprising that such a large integer point comes from the square of a small unit. This is kind of interesting. It's very unusual that this happens. And in fact, Zagier's point, it's not even a generator of the Mordell-Weil group. It's twice a generator plus a torsion point. So it's amazing that twice a generator, which has a large denominator plus a torsion point, would give you an integer point. I mean, this kind of thing rarely ever happens. So this is a highly unusual situation. Anyway, that's all I wanted to share. I'm sorry if I went over by 1 minute. Thank you.
Thank you very much, Gary. No problem, the 1 minute. We have time for questions or remarks. So please indicate it in the chat if you have questions. Yeah, there is Istvan Gal. Okay, thanks for the nice talk. Okay, also expressing thanks. Are there questions, remarks to the contents of the talk? Seems to be not the case. Or someone typing? No. So Gary, thanks again for this talk. Enjoy the snow in Ottawa and see you hopefully somewhere in reality in the future. And we have a break here, say of about 5 minutes, and then we meet for the last talk of today by Ilya Shkredov from Moscow. So we have a huge time difference from Ottawa to Moscow, and see you in 5 minutes. Bye-bye. Zaremba's conjecture and growth in groups. Please start with your talk.
Thank you very much. Thank you for the invitation. I want to say a few words about the connection between Zaremba's conjecture and growth in groups. So first of all, let me remind this rather well-known conjecture from the theory of the continued fractions. So we consider the continued fraction expansion in the following expression, as J are positive integers, they're called partial quotients. And the Zaremba conjecture asks the following questions. Let's fix a positive integer q, and we want to find the numerator a, such that a is combined with q, such that the ratio a over q, if you consider the continued fraction expansion of this ratio, then all partial quotients are bounded by some constant. Zaremba conjectured that this constant equals 5. So one more time, for any fixed q, for any fixed denominator, we want to find a new numerator a such that a over q has all partial quotients bounded by some constant. This 5 is because of numerical experiments for small numerators q. You see that Sj can be equal 4, but maybe if one just threw away finite number of q, then actually maybe this constant equals even 2. Okay, nevertheless, we are very far from this conjecture, and the best result in this direction is due to Korobov. But let me say a few words before this about the motivation of Zaremba, why he needed in such strange hypothesis. So his motivation was from the theory of numerical integration. Suppose that we have a function on a d-dimensional cube. Suppose that this function f has bounded variation, and we are trying to calculate the integral of this cube, the integral over this function f, choosing a finite number of points x. So x is a finite set, and we want to approximate our integral by this finite sum. Then a classical Cox-McLaughlin inequality says that this difference can be estimated as the ratio and the discrepancy. What is the discrepancy? The discrepancy is a very natural object. I take any rectangle R and calculate the frequency of appearance of my set X in R. So I consider cardinality of the intersection of X and R over size of X. And after that, I'm subtract just the measure of my rectangle. And after that, I take the supreme. So it's a classical inequality. The ratio depends on function. We have no influence on this parameter. But the real question here is how to find this set X with small discrepancy. So that's the question, and we have a lower bound. It's another famous result of Wolfgang-Schmidt, who says that actually there is an untrivial lower bound for discrepancy, and you cannot find your set X ideally. So any sequence of points has a non-trivial bound for its discrepancy. So for any finite x, discrepancy is greater than log x over x. 1 over x is a trivial bound, but there is this non-trivial factor, log x. So that's the lower bound, and we want to find the same upper bound. And I should say that if I take my set X to be a random set, then the discrepancy will be very nasty. The discrepancy is more or less 1 over square root of X. And thus, my X should be non-random and some specific set. So the Rambo suggested the following winding of two-dimensional torus. From this moment, my dimension is just 2. So I consider just square, 0, 1 squared. And let me take 2 parameters, A and Q, and consider the following discrete winding of the two-dimensional torus. So it has Q points, and Rambo proved that the quality of this X in the previous sense, I mean, in this Koxma-Glavka inequality, depends on the continuous fractional expansion of A over Q. More precisely, if A over Q has these partial quotients and M is the maximum of these partial quotients, then the discrepancy can be bounded in this way. And you see that if my M, this maximum, is really constant, then this multiple is constant, and you see that the upper bound coincides with the lower bound of Schmidt. So that was the motivation of Zaremba. Is it true that for any Q I can find A such that all partial quotients of A over Q as J are bounded by some constant M? If so, then I obtain an optimal result for discrepancy, and this optimal result is attained on a very concrete and natural, actually. Okay. So Kurobov proved that this constant M can be taken tending to infinity, unfortunately. So he proved in the case of Q equals a prime number, it's a very important case. He proved that there is H such that all partial quotients of this ratio A over Q are bounded by logarithm of Q. And for composite Q, this result was repeated by Rukavishnikova. And actually, both Korobov and Rukavishnikova results take this numerator A in a random sense. So for typical A over Q has all partial quotients bounded by logarithm. Rukavishnikova obtained a series of probability results in a probability sense, like central limit theorem for partial quotients and so on. For example, and this demonstrates the essence of the results, that say the number of A which account prime with Q and such that maximum of all partial quotients of A over Q is greater than T is bounded by log Q over T. So once again, typical A gives us logarithm for M. Okay, so it's the best result at the moment, and even taking small of logarithm of p is a so for specific q, the random conjecture is known to be true. It's a famous result of Niederreiter, who proved that for a specific q, say q equals 2 to the n or 3 to the n, you can take even m equals 4, and for 5 to the m equals 5. And there are another results in this direction by other mathematicians who takes other sequences of q, not exponentially growing, but even faster. And more or less all these results are based on the following idea, so-called folding lemma. There are several variants of folding lemma. I just mentioned one of them. So if I consider my continued fraction expansion, I can write the numerator and the denominator like two polynomials, and these polynomials are called continuants. And our problem, the Rambus conjecture, says that for any q, there is a continuant S1 as S with bounded as J, such that this continuant is exactly equals Q. So is J are bounded, and we want to represent Q as a continuant of these partial quotients. So there is a formula, a palindromic type formula for continuants. It's very easy to obtain it. So if I have this almost palindrome, you see these parts are equals in reverse order. Then for any x, I can calculate this continuant in this way. So you see, after that, I can use induction, right? So if my q is 2 to the n, say, then if I represent q, some q as a continuant with S1 as J, then by this formula, I can represent the larger continuant. And my new q will be what? 2 to the n squared, right? Times, I can choose x equals 1, say, or 3. And after that, I obtain this result with 2 to the n. Of course, there are some technicalities here, but the idea is this. So recently, rather recently, there is it was a huge progress in the Rambus conjecture by Bugan and Todorovich, who proved that the Rambus conjecture is true for almost all q. So they considered q from the segment from 1 to n, and asked, is it true that for this q, the Rambus conjecture holds with some constant m? And they showed that for almost all q, the Rambus conjecture takes place. Moreover, it holds for q, the number of such q is greater than n minus this very small error term. Okay, and you see this error term is very small. For example, from from this result follows that there are infinitely many primes for which the Rambus conjecture takes place. And moreover, this dependence on m and big O can be calculated in a concrete way. For example, if one takes m equals 50, then they show that there is a positive proportion of such q's such that the Rambus conjecture holds for. After that, their results were improved and generalized by many other authors, and actually simplified by Khan and Farlenkov. They simplified not the whole paper, but some parts of it. For example, the best result in this direction for concrete M belongs to Igor Khan, who proved that if M equals 4, then for all but smaller of n numbers of Q, Zaremba's conjecture holds. Okay, so but maybe this result holds for M equals 2. Okay, so what was the motivation? Why do we believe in this conjecture? This very strange conjecture. It can be explained in a more general context of Fuchs groups, but for Hensley, who gives us a heuristic and explanation, Hensley considers the following real dynamic of Zaremba's conjecture. So he considered the following set of real numbers. So alpha belongs to the segment from 0 to 1, all Sj are bounded by M, and then it was a result of Hensley that the Hausdorff dimension of this set can be estimated in a very nice way. For example, W2 equals this number is slightly greater than 1/2. Actually, it's important for us that it's greater than 1/2. And we see that real numbers with partial quotients which are 1 and 2 has rather large Hausdorff dimension. This asymptotic was known by Hinchen in 30s. Actually, for us, it's be sufficient to know that Wm is 1 minus big O of 1 over M. Okay. So Hensley considered a slightly more general situation. He treated this alpha like infinite words, as J belonged to a certain alphabet. In this case, the alphabet is just numbers from 1 to M. And he asked the following question: suppose that we have a finite set A, it's our alphabet, and suppose that Hausdorff dimension of the corresponding counter set is greater than 1/2. So now my set of real numbers satisfy the following property: as J belong to alphabet, to fixed alphabet alpha. Then, if I have the following alphabet, the following set of real numbers, then the Zaremba's conjecture takes place for all sufficiently large Q. So for all sufficiently large Q, there is A such that all partial quotients of this ratio belong to my alphabet alpha. So it's a more general conjecture, but nevertheless, there is an interesting restriction, 1/2. Yes, Hausdorff dimension is greater than 1/2. And I will explain you the heuristic of Hensley, which explain why we can believe in the Zaremba conjecture even in this strong and general form. Actually, in this strong and general form, this conjecture falls, and it was showed by Bulgan and Kantarovich, but it falls by some a little bit trivial reasons. Just there are no some natural congruence conditions on my counter set. So if this condition holds, maybe Hensley conjecture takes place. Okay. So why do we believe in this 1/2, in this Hausdorff dimension greater than 1/2? Hensley derived the following consequence of his result about Hausdorff dimension. He considered the following discrete, now discrete set, discrete two-parametric set. So he considered all ratios of the form U over V such that all Sj are bounded by M and U and V run over 1 from 1 to Q and U and V are compressed. Then it's very easy to show that size of this set can be estimated, can be calculated actually with very precise bounds, with perfect bounds. The size of this two-parametric set is just Q to the 2 Wm, that Hausdorff dimension. And actually, it's also rather well-known and general fact for general groups. But nevertheless, from this point of view, we can look at the Rambert conjecture as a question about one parametric set. So now we fix the denominator, say a prime p, and a runs from 1 to p minus 1, and we again want to find Sj such that all partial quotients are bounded by some constant. So if we believe in the uniform distribution in the denominators, then we need to just divide the previous bounded by the number of the denominators. So p to the 2 Wm over p. And we obtain the following quantity. And you see that if the Hausdorff dimension is greater than 1/2, then this quantity tends to infinity. And in particular, size of my Zaremba set tends to infinity. So that was the motivation of Hensley. And you see, it doesn't depend on any alphabet here. Just we need that the Hausdorff dimension is greater than 1/2. So our first result with Nikolai Mashiritin and Brandon Murphy, we proved that this heuristic of Hensley holds in the sense that there is the same upper bounds for size of Zaremba set. So for any epsilon, for any error epsilon, there is M such that the following upper bound takes place. So you see there is 2 Wm minus 1 plus the error term. And moreover, we proved that actually one can obtain Zaremba's conjecture if an interval, a very small middle interval will be removed. So for any prime p and epsilon, there is M such that if I consider the continued fraction expansion of a certain a over p, then all Sj can be taken less than M out of this middle interval of size epsilon s. So in some sense we are close, epsilon close to the Rambert conjecture, but actually we don't know what to do further. So now I want to talk about the methods. Surprisingly, the methods use growth in groups. We use the following very beautiful theorem of Harald Helgot, who proved that if I have a set of matrices with coefficients over Fp and the denominator equals 1, and suppose that my set generates SL2 of Fp, then either a cubed equals SL2 of Fp A cubed is the set of all possible triples, products A1 times A2 and times AB. Or this triple set grows exponentially fast. So size of A cubed is greater than 1, A to the power 1 plus C, where C is an absolute constant. So it's a growth result, very strong exponential growth result in groups, in one group, but after that Hilbert's result was generalized in several directions. And actually this result implied the following result on uniformity, which is even more surprising. So Bugan and Gambert showed that if I have a set A which doesn't belong any subgroup, any cassette of a subgroup in a very strong sense. I mean that if I consider any cassette of any subgroup H, any proper subgroup H, then the intersection of A and this cassette is less than A. So A doesn't live in any cassette. Of course, it implies that A is a generated set, but it's more strong to the assumption. So if so, then actually we will see the uniform distribution. So the number of representation of any S like a product of elements of A. Of course, by Hilbert's result, we know that A generates SL2 of Fp, and in a very fast way, because we have exponential growth. So moreover, after exponential number of steps, we generate SL2 in a uniform way. It means that there is the following asymptotic formula. We have the expectation plus the error term, which depends on this K. So it's a very nice result, but actually it's a consequence of Hilbert's theorem. They used one more tool here. They used the fact that the dimension of all irreducible unitary representation of SL2 of Fp is at least p minus 1 over 2. It's a famous result of Frobenius. And actually, they prove the very general fact that if I have growth in Hilbert's sense, and plus I have quasi-randomness in the sense of Gauss, it means that the dimension of all not trivial representation is greater than size of any group G to the epsilon. So now I am able to group G. Then actually these two facts automatically imply the uniform distribution. Okay. Okay, so I will skip this slide. Let me say now a few words about our new results. And how. So our new result with Nikolai concerns the so-called modulars of the Rambo conjecture. This question was considered by Hensley, who obtained some results in this direction. So in this formulation, I have a prime P, and I want to find Q, which is divisible by P. So automatically Q is larger than P. But it's not so larger than P. So Q is somehow comparable with P. So size of Q is big O of P to the 30. Then I can find A, which is compared with Q, such that all partial quotients of A over Q are bounded by some constant M. So once again, for any P, I find Q, which is comparable with P, and all partial quotients of a certain A over Q are bounded by M. Moreover, we proved with Nikolai Mashiitin the following result about partial quotients bounded by 2. So it's very interesting. There is a huge absolute constant C, such that for any prime P, such that Q is divisible by P and Q is comparable with P in this way, I can find A such that A over Q has partial quotients bounded by 2. Yes. So a new result of mine is the following. For any epsilon, there is a constant m dependent on epsilon only. And for any prime p, I can find q, which is so comparable with p that all partial quotients of A over q are bounded by m. So you see that it's somehow the limit of the previous method. Epsilon equals 0 gives us the Rambus conjecture, literally. Yes, and I want to talk about how to prove this result and our previous result with Mashiitin. Using growth in groups. Again, in our new results, we use growth in groups in a deeper way. So let me say a few words about a little bit more general context. I want to study growth in so-called Chevalier groups or groups of Lie type. For us, these words are synonymous. So we know from the classification of finite simple groups that there are 3 infinite families of groups. The prime field, the alternative groups of Lie type, and 27 sporadic groups. So for us, we are interested in these third families, ensemble of groups. They are all classified, of course. There are classical groups, SLN, unitary group, and so on, orthogonal group. And there are non-matrix groups, and also there are some exceptional groups like Steinberg and Suzuki groups. There is a formal definition, but I will skip it. So for us, let's consider the simple situation of SLN. So we are interested in Borel subgroup. It's the standard Borel subgroup is a subgroup of the upper triangle matrices. And we are interested in parabolic subgroups. By definition, a parabolic subgroup contains a Borel subgroup. So any subgroup of such type or conjugates of this, the upper triangle subgroup. So in the case of SLN, this family, it's very easy to describe. It's just the matrices of the following form. J are square blocks. Actually, it's the only, I would say, understandable subfamily of subgroups in Chevalier groups. This n-1 is called the rank of SLN. In any Chevalier groups, there is a rank. There is a famous conjecture of Barber, which says that any finite simple group actually generates in a very fast way. So for any set which generates any finite simple group, for example, in a Chevalier group, actually it generates this group very effectively. So I need just in this number of multiplications such that a to the n equals g. So if a generates g in principle, then it does it very quickly. And the conjecture, Baba's conjecture is known to be true for groups of Lie type. It's a generalization of result of Hilgard by Breuer, Green, Tao, Piper, Saba. They prove that this exponential growth holds for any finite supergroup of Lie type or for any Chevalier group. And in particular, it implies Baba's conjecture for such groups. But actually, these results works just for groups with a small rank, because you see this constant depends on rank. So for very large groups, or for alternating groups as well, this theorem gives. Okay, so we know something about growth in Chevalier groups, but in our particular case, one more result. What do we know in general about Chevalier groups? It's a generalization of Frobenius result about a representation. So it's a theorem of Lanzo-Rizaitz, who say that actually for any Chevalier groups there is an analog of Frobenius theorem in the following sense: if R is the rank of my Chevalier groups G of Q, then the size of all minimal representation is greater than Q to the R. So this Q to the R, it's a very natural quantity. If I consider the maximal by size parabolic subgroup, then Q to the R is just the index of this subgroup. And it means in particular that this bound is optimal. Yes, and it says also that there is a gap between sizes of all subgroups in Chevalier groups. There is a whole math groups G of Q, and after that there is the maximal parabolic subgroup, maximal by size parabolic subgroups, and after that smaller subgroups. So by some reasons which are connected with the Rambus conjecture, I am interested in the following question. I'm not interested in generating the whole group, whole Chevalier groups or whole SL2. I am interested in generating a parabolic subgroups. So I have a set A, and I want to find a non-empty intersection with a parabolic subgroup H, rather large. Of course, if I don't know Baba's conjecture, then there is nothing to ask. But I am formulating a wicked question. I want to find an element in my orbit A to the n belonging a rather large, very large parabolic subgroup of G of Q. So that is an algebraic question. And our first result in this direction is the following. So from Lanzo-Rizaitz, there is the following growth result. If I have a set of size slightly larger than size of maximum parabolic subgroup, then I generate the Chevalier group in a very effective way. Of course, if I take this maximum parabolic subgroup, then I do not generate G to the Q. But if I take larger subgroup, larger set, then I generate the whole group. That's the first result. That's a simple consequence of Lanzo-Rizaitz. And I want to underline that this set is arbitrary. I don't require that A generates G of Q because then it's trivial. It's any set. So our first result is the following. Suppose that I want to find non-empty intersection with a to the n and any parabolic subgroup. Then actually I can improve this restriction. I consider any set of size p max q to the delta over q, and for such small sets, anyway, a to the n intersects p. So basically, I improve this classical result by this one, and this one is very important for me. So another result of gross resolutive parabolic subgroups is the following. What can we say about product of any set and any parabolic subgroup? So if I consider a set of this form, x times p, so it's a union of cosets of A, right cosets of A, then of course multiplied by p from the right, I obtain A. So there is no growth here. Similarly, if A equals py, then multiplied by p from the left, I have no growth. But if I multiply simultaneously from left and from the right, then there is a growth. So for any set and for any parabolic subgroup with some mild, I need in some mild restriction, say the intersection is empty, not important, then this maximum actually grows. So for example, if A is less than P, then this maximum is greater than A times square root of Q. So I have a growth by square root of Q. So let me apply these results to the Rambus conjecture. So in the Rambus conjecture, in the Rambus conjecture, we associate with continuous fractions the following set of matrices. So if I have the fraction PS over QS, then I consider the following product. It can be written this way. And the determinant of these matrices are plus minus ones. I obtain a set of matrices from SL2 of FP, more or less. And of course, in the Rambus conjecture, I am interested in Sj bounded by M. So that's my restriction. And also suppose that QS is less than it's the largest element in these matrices. So suppose that all elements here are less than P. So by Hensley's lemma, the size of A it's easy to calculate. By Hinch, we know that this quantity is P2Wm is just P to the 2 minus big O of 1m, so it's a little bit less than P squared. So A is large, but not so large. To compare, size of SL2 is P cubed, and size of our standard Borel subgroup is P squared. So it's a little bit less than P squared. So A can lives in some Borel subgroup. So after that, once again, I have the following set, and suppose that A to the n contains 0. Say this element of my matrix is 0 modulo P. So I consider this orbit A to the m, and suppose that I find this 0 in my orbit. Then just by multiplication, by matrix multiplication, I know that QS minus 1 is bounded by 2p to the n. QS minus 1 is divisible by p. And PS minus 1 over QS minus 1 has partial quotients bounded by m, just by definition. So this problem, this modular problem of Hensley, can be interpreted, reformulated in the following very classical way. So I consider the standard Borel subgroup, and I want to find a non-empty intersection of my orbit with this Borel subgroup. So this why I am saying that this is a classical formulation, because Borel subgroup, it's a very structural object. It corresponds in analytical number theory. It corresponds to arithmetic progressions, more or less. And A is more or less a random set. I will show you at the end that actually A is a random somehow. So I am interested in finding non-empty intersection of A of random set with a structural set, and moreover of some power, like some set, yes, some power of A with a very structural set. It's a classical problem. But and maybe it's the most attractive point of our proof that this non-commutative problem actually is a little bit is easier than the classical analytical problem, because in this point of the proof, non-commutativity helps us. I mean the following. So we want to find an empty intersection by multiplying this intersection from B from the left and from the right. I see that this problem is equivalent to this one. And you see, I have BA and AB here. So I have two different products of A. And by our growth result, the AB or BA must grow anyway. And after that, I broke this square P squared barrier. Now I am larger than P squared. And I can apply Lanza-Rezais results or Hilgot's results. And we did it with Mashiitin in our previous paper. So what about modular Hensley conjecture? In this situation, my set A is thinner. The Hausdorff dimension just a little bit greater than 1/2. So size of A is P to the 1 plus epsilon, more or less. Here, another classical result helps us. It's a structural theorem of Dixon. So he classified all subgroups of SL2 of FP. There are just Borel subgroups that conjugates and subgroups of Borel subgroups. Borel subgroup has size P squared. After that, there is a gap. So the another series of subgroup have size P plus minus 1. And after that, there is another gap. So there are just several finest ugly subgroups like A4, F4, A5. So just by size, my set A, the orbit of A avoids all these the dihedral subgroups and these finest subgroups. So my enemy now it's a Borel subgroup and its conjugates, and we know the following general results. So if I have the following assumption, if my A is so large, then I intersect all parabolic or Borel subgroups. So you see that because of this one, our assumption A is greater than P1 plus delta just coincides with this restriction, and I find a non-empty intersection of A to the N and any actually Borel subgroup B. So once again, we obtain using this technique, we obtain the following modular Hensley result. Yes, and as for this result with epsilon, we need in much more careful analysis of my set A. Actually, in the terms of analytical number theory, I calculated all exponential sums, all representations of this set A. I proved there is an exponential cancellation here. Methods of additive combinatorics were used in this derivation. Plus, of course, Helmholtz types results on growth in SL2 and other combinatorics. So we have this result, and that's all. Thank you for your attention.
Yeah, so thank you very much for this very rich lecture. So, of course, it's open for discussion. And let me start with two remarks. Remark one is you mentioned this result extending Korobov from prime moduli to general moduli of 2007 or so. If I remember correctly, Gerhard Larcher in the 80s had already such a result. It's published in the Monatshefte. I don't remember the citation correctly, but it's somewhere in the Monatshefte.
Oh, I have a comment on this.
Thank you.
Sorry.
Yeah?
I can give a comment.
Yeah, please, Nikolai.
Gerhard Larcher gave a result about discrepancy. He improved essentially discrepancy.
Yes.
He improved discrepancy,
yes.
log square bound to log bound.
Yes.
This is, but not for composite numbers. It is in Monatshefte indeed. It is a wonderful paper. And when Bykovsky proved a general result for arbitrary dimensional, I was the person who advised him to add the reference to Larcher.
Okay, so this is related but not the same, yes?
It is not the same. It is not the same. It is about discrepancy. So the problem with discrepancy is easier. For discrepancy, we have not log square, which follows from Zaremba.
Clear.
Times log, which follows from Larcher.
Yes.
It is a wonderful result indeed. I like it very much. So
okay, so thanks. This was my first observation. The second observation is just an advertisement. We had Kontorovich here in our theorem program as an online lecturer in October with a series of 4 lectures on Zaremba conjecture. And of course, he gave talks on his work with Bourgain. So on the density 1 result. So this is very nicely complementary to what you have achieved here. So thanks again for that. And maybe there are other questions or remarks. No other questions. Maybe they show up until tomorrow morning. We meet tomorrow in our time 9:20, so in Moscow it's 11:20. And I should also say that I have to express many thanks to the theorem video team and to Celine. They managed to get discussion rooms, as Nikolai suggested. You should have got them emailed just some few minutes ago. They explain how to use these online virtual discussion rooms for establishing smaller groups. So Nikolai, please try it to organize a small group. Then we know tomorrow if it works well.
Just now with Ilya. Ilya Dmitrich, давайте попробуем.
Okay. Good. So see you tomorrow and good evening. Yes. Bye-bye.
Thank you. Thank you.